Well, good afternoon, everybody. So this lecture will take the place of this Tuesday's lecture since I am out of town. And I will be back for Wednesday and Thursday of this week. And so we are continuing talking about rate laws, something we were talking about just before your midterm exam. And I just want to go through one more with you, and then I have a few questions in Chem 101 that we can go through. And so a question like this, where you've got a potentially balanced equation, you've got these whatever coefficients in front of the reactants and products, and you're asked, what is the rate law? And so again, if you aren't given any information here, like a table of data, you can't answer the question. Okay, so you need this to determine what the rate law is. And so if we write, this general form, so it's just a raised to some power, and then b raised to some power. And we really want to know what these are, okay, those exponents. And so we are going to compare experiments where only one of the reactants are being varied, and the other one is held constant. So if we look at experiments 1 and 2, B is held constant and A is being doubled, right? So if you do 0.2 divided by 0.1, you get 2. And then if you do 4.2 times 10 to the minus 4 divided by 2.1 times 10 to the minus 4, you see that that also is going up by 2. Okay, so that's going up by 2, that's going up by 2. And so regarding A then, because B is held constant, so if A is doubled, and then the rate is also doubled, then A has to be 1, right? 2 raised to the first power is just 2. Okay, so far we have got that. Okay, and so now we want to compare experiments where B is being varied and A is held constant. So we'll look at 1 and 3. And in this case, you are doubling B, right? Because 0.03 divided by 0.015 is 2. And then if you punch in your calculator 8.4, I'll do it here with you. So 8.4 to the fourth power divided by 2.1 to the fourth power. You see that that's going up by a factor of 4. Okay, and so now A, we already have A, so B, I'm sorry. So if we are doubling B, and the rate okay, so this is what we've done to the concentration of B. It's just been doubled, right, here to here. And the rate has gone up by a factor of 4. Okay, so now hopefully everybody can see that B has to be 2, right? Or 2 to the second power is 4. Okay, so your overall rate then is some constant. A, we said it was just a power of 1, and then B, we said was a factor of 2, or exponent of 2. Okay, so this is your rate law. Okay, and we would say it's first order with respect to A, and second order with respect to B. Okay, just because it's a 2 there, so that's second order, and then 1 means first order. Okay, and then if you add these up, it's third order overall. Okay, so we'll get to that again on Wednesday. We'll talk about what that really means. Okay. All right, so before we get into these Chem 101 questions, here are the important aspects. So about a rate law, that the exponents have to be determined from actual data. Okay, so you can't get it from the balanced reactions. And then comparing changes in individual reactant concentrations with changes in rate shows how it's dependent on each concentration. So we just do that in turn with both of the reactants and then find out, what is the rate with respect to A, and then look at another couple experiments, then you get the rate with respect to B. And reaction order is always defined in terms of reactant concentrations, never product. Okay, so that is another really critical term or aspect here, is that notice our original rate law just was talking about A and B. So C and D will never, like products, will never appear in the rate law. Okay? All right, well, with that, I loaded up, since it's not live, I wanted you to still get opportunity to get participation points, and so I put, I think 5, so 5 rate law questions in practice for you in Chem 101. And so let's go through these. All right, so rate law 1. Here we go. So which of the following represents the rate at which ClO2 minus, we'll just call it, is appearing in the reaction below? Okay, and so this is where you're illustrating things, comparing kind of apples to apples. And so just to remind you, anything on this side is disappearing, so it will have like a negative change in concentration. These are appearing, so they're going to have positive concentrations. And so just to get you started, if you look back at your notes, remember if you have a coefficient in front, you just take the inverse of it. So we could write the expression for ClO2, not ClO2 minus, that's this guy. But if we want to know this one, we would say that it is minus 1/2 the change in concentration of ClO2 with respect to time. Okay, and that is equal to minus 1/2 the change in concentration of OH minus with respect to time. Okay, so that's how you would do these products, or reactants, sorry. And so now the products, we could say then that these are equal to, and maybe pause the video instead of me giving you the answer. Pause the video and see if you can come up with the expression for ClO2 minus, how that would look like in terms of these expressions here. Okay. All right, so assuming you pause the video and we're back on it here, you could say, since ClO2 minus has a 1 in front of it, it's just going to be the change in concentration of ClO2 minus with respect to time. Okay? All right, and you could say that's the same thing as the change in ClO3 minus with respect to time, or the change in water with respect to time, because they're all 1s in front of them, okay? And so now you're just really looking through this list and seeing which ones make sense, okay? So the rate at which this is appearing, so we want to know, so this one is the same as something else, or if this is actually on the list itself, which I don't think it is. Okay, so what about this one? So this is saying that this is the same as plus 1/2 the change in ClO2. Okay, so this is not correct because you need a negative in front of it, right? That's going away. Okay, so it can't be that one. What about this one? Water going away? Nope. It needs a positive instead of negative, so that's wrong. this one, the positive change in OH minus. Well, that's wrong for a couple reasons, right? It should be a minus 1/2. Okay, so it should be negative, and it also should have a half in front of it. So that's really wrong. And then this one, it's closer, I guess, but it should be a negative 1/2 instead of positive 1/2. And so I guess by default, it has to be this one. Let's just confirm it's positive ClO3 that's appearing and positive ClO3. Okay, so this one would be correct because it matches this. Okay, so this is very typical of a question you're going to see on your second midterm. So nothing like, remember we did one in lecture last week that was really, really complicated. You had to like multiply by factors, things like that. This is the variety that you'll see, so more straightforward. All right, so that's rate law 1. Rate law 2. Okay, what is the rate at which bromide ion disappears in the reaction below if the rate of disappearance of bromate is, and then you're given the certain concentration versus time. And so the actual rate that is going away. All right, so for this, you're concerned with bromate and bromide, so you should write those two expressions down. Okay, so the rate of disappearance for bromate would just be the minus change in concentration of BrO3 minus with respect to time. Okay, and that is equal to, with bromide, minus 1/5 the change in bromide. Whoops. Change in concentration with respect to time. Okay. And so if you're given this, okay, is 0.020 moles per liter per second, okay, then what do you think you would do to get that concentration? Okay, so they're both going away, so they're both negative, but this one is 1/5. Okay, so it's a minus 1/5, and this one is just a minus 1. Okay, and so again, pause the video, think about it a little bit, and then we'll come back. Okay, all right, so we are back, assuming that you paused. And so what you can do here is, since this is 1/5, what if we multiply everything through by 5? Right, so both sides by 5. Okay, and so what that does is it says that this, okay, is essentially 1, and this is 5 times the rate, okay? And so in other words, you can say that the change in bromide concentration with respect to time is equal to 5 times the change in BrO3 with respect to time. Okay? And so in other words, we do 5 times 0.020 that. So that should be 0.100. Okay. I guess I added another 0 in there. Okay. And so just to maybe walk you through the math a little bit. Okay. So we just essentially substitute 0.02 for the bromate. Okay, and then you solve for the bromide. Okay, and so bromide is 5 times the 0.02. All right. So another question that is fairly typical of something that that you may see on either the midterm or the final. All right, so rate law 3. And here we get into determining the rate law based on data. Okay, and so this one, you want to know the value of the rate constant. Okay, and so for us to do that, we first need to figure out what is the rate law itself. Okay, and so the rate law is going to be some constant, and then our reactants are A and B. Okay, and so we have to figure out what those exponents are, and so let's compare experiments 1 and 2 first. So B is held constant, and then you look at what this is doing. Okay, and so if you do 0.450 divided by 0.150, we get 3. Okay, so this has gone up by a factor of 3. And then if we do this divided by this, so that's 1.01 to the 4th power, negative 4, divided by 3.38 to the 5 minus. That gives you 2.988. So pretty close to 3 as well. So that has gone up by 3. That's gone up a factor of 3. And so we can say that with respect to A, it is first order. Okay, so in other words, if we had an effect of tripling A's concentration, and then the whole rate tripled, A has to be 1. Okay, so K. All right, so that's with respect to A. And then for B, let's look at maybe 2 and 3. Okay, so now A is held constant. And here it's kind of decreasing. So you can either like go this way. I always go so that it's increasing. So I'll compare, I guess, experiments 3 with 2. And so from here to here, it's going up by a factor of 2. And so now let's divide this one by that one. Okay, so that would be 1.01 e to the 4 negative divided by 2.54 e to the 5 minus. And that's a factor of 4. Okay, so here you're doubling, but this goes up by 4. And so as far as B, that now is 2. Okay, so therefore the whole rate law is K A B squared. Okay? And again, you needed to get data to get this rate law because, if you look at the actual equation, you've got a 2 in front of the A instead of the B. So there's no correlation at all between these exponents and the balance coefficients here. So you need this data to determine this. Okay, so now we've got the rate law, but it's actually asking for the value of the rate constant. And so for that, all you do is pick any experiment. Okay, so all these experiments will follow this rate law. And so just pick anything. And so just pick experiment 1 and just substitute values in for everything, the rate, A and B, and then you solve for K. Okay, so using experiment 1, we have 3.38 times 10 to the minus 5, okay, that's the rate, is equal to some constant, And now A is 0.15, and B is 0.3 squared. Okay? And so I would multiply these first and then divide both sides by that. Okay, so therefore K is equal to, we'll do 3.38 times 10 to the minus 5 divided by that. To be a little explicit about it, okay? So let's see, so 0.15, and we've got 0.3 squared times that, and divided by, okay, so I get therefore, so K is 2.50 times 10 to the minus 3. Okay. And so I guess that would be A. All right. Now, with respect to the unit, we're going to talk about this a little later today. But with respect to the unit of the rate constant, it depends on what the order of the reaction is. Okay, and so the rate, okay, so if I just rewrite the rate law here for this particular reaction, okay, the rate is always going to be in units of concentration, so that's moles per liter, per second, okay? And then these are always going to be in concentrations, okay? So anything in brackets are going to just be concentrations, okay? And so if we kind of carry this through, we've got m divided by s is equal to k, and then we've got an m, and then another m squared here, okay? And so then we can say that's k, whoop, that's a ugly k, m cubed, okay? And so then we can divide both sides by m cubed. Okay, and what you get out of that then should be, that's gone, and so you really should have 1 over m squared second. Or I guess this is in minutes. Whoops, so it's in units of time, I guess. Yeah, but yeah, I guess I didn't read the question carefully, so it's per minute here. But I guess, if this were minutes, okay, then it's concentration per minute. Okay, and that is equal to the rate constant. Okay, so this is 1 over m squared times time, a unit of time. Okay, and so that's just really something, again, we're going to talk about a bit later today. All right, so that was rate law 3. Rate law 4. Okay, so here you are told what the rate law is. By what factor does the rate of the reaction increase when both A and B are doubled? Okay. All right, so that's the rate law. So if we change that by a factor of 2, and that is also by a factor of 2, then the rate, I guess it's not, I guess some rate constant. Okay, but does everybody see that this will go up by a factor of 4 then? Okay, if they're both doubled. Okay, so again, a very typical question for exams. I could have said, what if you, you double A and you triple B. Okay, then you would just say 2, 3, so then your rate is going to go up by a factor of 6. Okay, so it's really that easy. Where it gets kind of more difficult is if you have like a second order or something like that. Then it would be 9 times 2, so your rate would go up by a factor of 18 in this case if it were a 2 up there. Okay. All right, so that's rate law 4. And then the last one for practice that I queued up for you is something that you're going to see on Alex. Okay, so this one, it looks same as what we've done many times already. A and B are your reactants. Okay, we want to know what those exponents are. And so, it's pretty straightforward to figure out what B is, right? Because you look at A here is held constant. Here you're tripling. And then you look at what happens here. So 2.55 divided by 0.85 is a factor of 3. Okay, so you triple this and you triple that. So we've got B is just 1. Okay? But then A is where the problem lies, right? Because you don't have any of these experiments where B is held constant. And so the strategy here is, since you already know the rate law with respect to B, you can figure it out by combining where both are actually changing. Okay, and so here's the strategy. Figure out what the rate is doing with respect to A here. Okay, and so 3.75 divided by 1.25. So that's a factor of 3. Okay, and then look at B for this experiment. So I'm comparing experiments 1 and 3 here. So this is going up by a factor of 3. This is going up by a factor of 2, right? 0.2 or from 0.1 to 0.2. So that's a factor of 2. And we already know that that is first order. Okay, and then look at what happens to the rate. Okay, so 5.1 divided by 0.85. That's a factor of 6. Okay, so then it becomes kind of a simple math problem, right? So what does A have to be if the rate is going up by 6? Well, it has to be 1, right? So 3 to the first power times 2 to the first power is equal to 6. Okay. All right, so the rate law then is K A times B. So first order with respect to both of those. So that would be this one. Okay, so hopefully those make sense. That kind of spans all the possible questions I could give you on exams. So yeah, so there you go. All right, so let's continue talking about, here we go. So the orders of reactions, okay, so with respect to different reactants here, I have to plug in my computer. There we go. Okay. And so if we have this balanced reaction and we find out based on data that this is the rate law, we would say then that the reaction order with respect to nitric oxide, or NO, is second order. It's first order with respect to oxygen, or third order overall. So you're just adding up these exponents. Okay, so this is the overall reaction order. All right, now this is where we get into units, okay? And so the units for K for this, okay, would be in, and if I write this out explicitly again, I think this is what we already looked at for this exact one. But just to show you, because here is seconds this time. And so rate is K and O squared times O2. Okay, so this is going to be in units of concentration per unit time. This is always just concentration, and that is always just concentration. Okay, so this is m to the third power times k, and that's m over s. Okay, so therefore k is equal to m s, and then we're dividing both sides by m to the third power, right? Okay, so we can take one away, cancel that out, and so we get then that k is equal to 1 over m squared times second. Okay, or you could write it as m to the minus 2 seconds to the minus 1. Okay? And so that would be for a third order reaction. Okay, these are the units for all the different. So for a 0th order, where we don't have, it doesn't depend on A at all. And let me show you how you would get that from data if it's 0th order. So that would be, let's say, we've got experiment 1 and 2, and we're doing like a concentration of A, and then the rate. Okay, and let's say this is 0.1, and this is 0.2, and this is 1 times 10 to the third, and then it's times 10 to the third. Okay, so in this data set, does everybody see, the rate law, in this case, you only have one reactant. Whoops, some rate constant times that. Okay, and so if you're doubling A, the rate does not double and it doesn't triple or anything like that. It actually stays very close to the same. And so we would say that the rate really does not depend on A. Okay, so we would say that it's 0th order, or in other words, that rate is just equal to the rate constant. Okay, so concentration doesn't even appear here. Okay, and so in that case, the value for the rate constant is just whatever the rate would be, and that is some concentration per unit time. Okay, so that's concentration per second. Okay, or writing it could be m second to the minus 1. Okay, and then for first order, you have rate, which is concentration per unit time, is equal to k times concentration. Okay, and so in that case, if we divide both sides by m, you just get 1 over s for the value of the rate constant. Oh, okay, or seconds to the minus 1. Okay, so that's for first order. And then for second order, like this, for instance. Okay, this is that as always. This is that. This is that. Okay, so essentially we are then dividing both sides by m squared. Okay, and so then we've got m over m squared times s is equal to k, or k is equal to 1 over m times s. Okay, or you could say m to the minus 1, s to the minus 1. Okay, and then we already did third order in the previous slide. Okay, so these are the units, and we will come back to this on Wednesday when we look at determining rate, the orders, and then what equations we have to use to do sort of some more complicated questions. So we'll come back to this. So kind of file this away. It's something you're going to have to know. You can either, I guess, memorize these or just derive them like I did. It's just really kind of a simple derivation to figure out, what is the unit for the rate constant. Okay, so here comes the complexity of this chapter. So these are called the integrated rate laws. And so I am not going to bore you with derivations here, okay? But for a first order reaction, this is the rate law, okay? So hopefully everybody agrees. So this is rate, some constant, and then you've got a concentration. So it's first order overall, right? And so you can then illustrate that as the negative change in concentration of A with respect to time is equal to K times concentration of A, right? So this is just another way of saying rate. Okay, so these two equations are identical. Okay, well, they're expressed differently, but they mean the same thing. Okay, and so what we can do with this form is we can integrate both sides. To take the integral of this side, take the integral of that side. Okay, and with respect from some initial to some concentration at time t. Okay, and we can get this form, which is called the integrated rate law. Okay, and so remembering maybe something back that you had in a previous math class, if you have something where it's natural log of, you've got a numerator or denominator, you can turn that into the natural log of the numerator minus the natural log of the denominator. Okay, so it's just the algebraic form here if you have natural logs, so the law of natural logs. Okay, and so you can turn this then into this expression. So let me kind of write that out. So natural log of A at time t minus the natural log of A at time 0, so your initial concentration, is equal to minus kt. Okay? And so then we can just take this over to the other side. Okay, and that's where they have this form of it. Natural log of A is equal to minus kt plus natural log of A naught. Okay, so this is at time 0, so this is your initial concentration, and this is concentration at a certain time. Whoops, go like this, at time t. Okay, some later time. All right, and so if you have it in this form, and by the way, all of these integrated rate laws I will give you on exams. Okay, so you do not have to memorize them. You just have to know how to use them. Okay, and so this will be given to you. And so does everybody see, when we're plotting things, we could say y is equal to mx plus b. Okay, and so your y-axis then would be natural log of your concentration of A versus t, okay, your time, and you're going to get a negative slope. Okay, so that's your slope of minus k. All right, and then your intercept is going to be the natural log of A at time 0, or your initial concentration. Okay, so by plotting up the natural log of concentration versus time, you can actually get what the rate constant is. Okay, and you can figure out what your initial concentration is if you're interested. Okay, and so you're going to do this in lab. We're going to, do different concentrations, and you're going to have different, at time, as time proceeds, you're going to figure out what the concentration is. To plot it, you're going to take natural log of all these. Okay, so you're going to calculate all those, and then you're going to plot this, the natural log of concentrations versus time. If it gives you a straight line, then you know that it's first order. Okay, so that's kind of broken down for you here. Okay, so this is just a plot of concentration versus time, and very typically it will not be linear. Whoops, I didn't mean to move it. Okay, it won't be linear. It's going to be like an exponential decay. Okay, and so by the way, if this is linear, then it's zeroth order. Okay, so let me write that down. I don't know if that's explicit in the, so if concentration versus time is linear, so just concentration, time, okay, then you have rate is equal to K. Okay, which I guess, whoops, it's actually not negative. It will be positive slope. Okay? But very typically and in lab, it will not happen that way. Okay, so it won't be linear, so then you will plot natural log of concentration versus time. Okay, and if that is linear, then it's first order with respect to A. Okay. All right, so this is just shown here. So this is just concentration versus time. This is natural log versus time. And you have a nice linear trend here. All right, so it's just shown here just with some data. So this is something you're going to do in lab, not this decomposition reaction, but for some reaction, you're going to just look at time. You're going to get this concentration. And then you're going to have to take natural logs of all these numbers. Okay, and then using Excel or whatever your favorite graphing program is, you're going to plot this versus time. Okay, and then see if it gives you a straight line or not. Okay, and then you can calculate the slope. Okay, and the slope here, so rise over run, okay, will give you K. All right, it's a negative slope, so the negative, you're taking the negative of this value will give you the rate constant. Okay, and just one thing to keep in mind for lab is that, if you get messed up with the negative, is it negative or what? The rate constant can never be a negative value. Okay, so just take absolute value of this. Okay, so it's 0.0017. All right, for half-life, which is very typical for radioactive decay, for instance, and all radioactive decay processes are first-order kinetics. And so this is how you would sort that out. Okay, so if this is our regular equation, okay, all you will say is that a half-life by definition is how much time is required for the reactant to drop to 1/2 of its initial value. Okay, and so if we start with 1 here, okay, then we have 1/2 here. Okay, so you can just pick numbers. Okay, so maybe if it makes more sense to you, you can start with 100, and now you're at 50. Okay, it's all really up to you, whatever you want to do to kind of plug values in. Okay, and so if you punch in your calculator natural log, I'm looking it at my calculator. There we go. Okay, so the natural log of 1 where did it go? There we go. So log to the E, in other words. So that's just 0. Okay, so ln of 1 is equal to 0. Okay, so what's nice about this is that this term goes away for half-life. Okay, and then we typically put a little sub 1/2 just to remind us that it's half-life here. And so if you do 0.5 natural log, okay, so the ln of 0.5 is equal to minus 0.693. Okay, and so in other words, it's minus 0.693 is equal to minus kt. Okay, and so the negatives go away, and so in other words, that expression, so this, okay, simplifies to, sorry for all the scribbling here, 0.693 is equal to kt, or t is equal to 0.693 divided by k. Okay, so that's your half-life. T 1/2 is 0.693 divided by k. All right, so we will talk about this and do some questions when we're back live together. Okay, so I don't want to go too far here, but I guess just to kind of show you graphically here what we mean by half-life, if this is your initial concentration, then after the first half-life, you've got half left. Second half-life, you've got half of that. And then you divide that in half again, and so on and so on. So you can have, after 4 half-lives, you've got divided by 2, now it's a quarter, now it's eighth, okay, then it's 16th, 1/16 of what you started with, etc. Okay, so we will look at, I guess, some questions related to first order integrated rate laws on Wednesday, and then we'll move on to second order. Okay, and so in lab, you're going to have to determine whether something is first order or second order by graphing things. And again, for our purposes in Chem 132, you will only have either first or second order reactions. We're not going to go into third orders. And so basically, you'll plot your concentration versus time. If that's linear, you know it's 0th order, and you can stop. If it's not linear, and then you plot natural log of concentration over time, and let's say this is still not linear, now you know that it's second order by default. Okay, on Wednesday we'll figure out what do you graph to determine if it's second order or not. Yeah, for lab, that's really what you're going to do. You're just going to plot things and then determine which one gives you a straight line or not. Okay, so hopefully everything makes sense, and if at all possible, I'm going to send out an email that you watch this before Wednesday so we can pick up right where we left off from this video. All right, so enjoy the rest of your day, and thank you.